Oh, hello, my name is Christian. Okay, so let's take a look at the problem here. This is a fun one, solving initial value problem by the Laplace method. So I did all the work on paper already. So let's go and take a look at what we have here. So this is the original problem, x double prime of t plus 3x of t equal to 2 cosine square of t. The initial values of x of 0 and x prime of 0 being 0. And you also mentioned there's a convention. Big X of s is equal to the Laplace transform of x of t. Okay, so, I put down a few formulas you might need to know. You might want to know reduction and also some common Laplace transforms to use. You can go either way for Laplace or inverse Laplace. And in general, the transform over derivative is this, but you only need a second derivative, so I gave you this one. Okay, so x double prime, I should say, of t plus 3x of t equal to 2 cosine square of t. Just reiterating the original problem. And then remember that the Laplace transform is a linear operator, much like your differentiation, your integration, those are linear operators. So they get applied to each of these. You can do scalar multiples, like here and here. And this is this step. This is where you would have to have rewritten the cosine square in a reduced, re-expressed manner. Okay, so continuing to do that, this is how, again, you would take advantage of the linearity of the Laplace transform. Here is where substitutions are being made. So x double prime of t is the inverse Laplace. Not its inverse Laplace, it's Laplace. S square of the Laplace transform of the function minus f times that first initial value you gave minus the second initial value you gave. And then again, the Laplace of x of t is big X of s. And then going through Laplace of 1, because you can't do Laplace of a half. It would technically be a half times the Laplace of 1. A half times 1 is a half. So you have to go off of that if you're trying to find the Laplace transform of a constant. So 1 over s, a half times 1 over s. And then cosine of 2t. Again, you go off the transforms that I provided earlier, look in the table. You find this. And here, notice how I re-expressed that term there as 2 squared instead of as 4. Makes it easier to fit into the formula. And then making the substitutions from the initial value, this is what you get. Further reduction on the right-hand side. Okay, doing that simplification gets you here. So it's a little more polished now. The right-hand side, you can go and take care of some common denominators, and also getting these expressions to be the same denominator. So you're doing that, and also combining like terms on the left-hand side, because you have big X of s. You can do that, s squared plus 3 times the Laplace of x of t, which is big X of s. Combining everything, you get to here, to this step. More simplification, dividing both sides by s squared plus 3 finally gets you here. Now, this is where you have to break this apart using a partial fraction decomposition. So your denominator has the terms of s squared plus 4, and s squared plus 3. S is distinct, linear. S squared plus 4 is distinct, irreducible quadratic. And s squared plus 3 is another distinct, irreducible quadratic. So 3 kinds of things going on here. This is how you're going to do the partial fraction decomposition. You have an a over s, bs plus c over s squared plus 4, because again, that's the irreducible quadratic. And you have ds plus e. You're trying to get the numerators to add up to 2s squared plus 4. So going through the algebra and the mechanics of a partial fraction decomposition, you would do all that, combine the like terms, and what you're going to do is to group all together the terms with s to some particular power. So order up all the s to the 4th, order up all the s to the 3rd, order all of the s squareds, the s to the 1st, the constants. And then what you can do is you can put those constants all together, represent them as a coefficient matrix, like this one. Notice how I have the columns going by A, B, C, D, E for those undetermined coefficients, if you will. And then you have the rows going by this power of S, fourth, third, second, first, then just constants. So this rightmost column should be representing 2s squared plus 4. So once you put that, and once you solve the system, or if you put in a calculator and put into reduced rational form, this is what you get. A is equal to a third, B equal to -1, C is 0, D is equal to 2/3, E is 0. So you have those, put them back into the partial fraction decomposition, and then this is where you can start to bring terms out to the front, like coefficients. 1/3 over s becomes a third times 1 over s. 1 over s is a kind of Laplace transform. You can actually take that, like textbook, and get its inverse Laplace back. -1s plus 0 is just minus s. Okay, s over s squared plus 4 is actually a readily read off Laplace transform. Then 2/3 s plus 0 is just 2/3 s. Bring the 2/3 to the front, you have s over s squared plus 3. And that also is readily read as a kind of Laplace transform. And inverse Laplace transformation is also linear. So apply it all the way across, bring out any coefficients out to the front. You can do scalar multiples like that. And what I did here, I was doing this on paper earlier, and I thought, okay, I ended up doing a little too much. If I were trying to get inverse Laplace transforms to find signs, then I would need to have done the little trick that I did here to somehow force a 1 up in the numerator, but I didn't need to do it because I just had s in the numerator from this step. So what I really need to focus on was just the fact that I really just had these s's to work with. And that meant I can find cosine as an inverse Laplace. So reading off of, well, first off, I have to read the bottom as s squared plus some constant squared. So that's the only re-expression I should have done is in the denominator. So over here, 4 is 2 squared. Over here, 3 is the square root of 3 squared. Doing that, and then going off the Laplace table, going the other way for inverse Laplace, that is how you end up at the final, well, that's just the application of the inverse Laplace transforms. The final simplification gets you to the final x of t. X of t is 1/3 minus cosine 2t plus 2/3 times the cosine of the square root of 3t. If you have any questions, anything I can clarify, please let me know. This is a very good problem, and it was an absolute pleasure to work on this one. I hope you found this helpful.